Now, in your career, the horizontal engine is going to be probably the most common that you end up having to deal with, especially if you're working in general aviation. That's what's out there, and that's what you'll end up seeing on a regular basis. However, there are some sectors of aviation that still use radial engines. They're older, very niche, nuanced places, but they still exist. I've worked on radial engines on de Havilland Beavers up in Washington. And you still may encounter them wherever you go. And it's still good for you to understand how it still accomplishes the same thing that a horizontal engine does, but the parts and pieces look a lot different because it's arranged in a circle as opposed to just being opposed to one another. So let's talk about the R680, the radial engine that we have here, and what its parts and pieces could potentially look like.
Now, there's definitely some nostalgia that surrounds radial engines. This was the first engines they ever put on actual airplanes. And a lot of this nostalgia is well earned. For a time, these engines were the most advanced and the most powerful engines that the world had at its disposal until they were displaced by the invention of the turbine engine. Now, they don't really work any different than a horizontally opposed reciprocating engine. This is a table that someone made of a radial engine, but that just shows how it actually operates. Notice that there's a crankshaft that moves around, that moves the pistons into place, and as the pistons move up on their compression stroke, a valve opens, letting in atomized fuel, and then a spark hits, causing the power stroke to come down and push the crankshaft, which ultimately spins the propeller. Just like the one that you see here that's attached to an R680 that is actually attached or that is mounted on a Boeing Stearman. Now, the Stearman was really popular back during early days of World War II as a trainer, and beyond more than just the Army, but also the Navy. Several uses for the Stearman to include crop dusters, and today the Stearman is a prized possession for the people that still have them that are flying. All of them powered by the old R680 engine, the old radial engine. Now, the way we start to break down a radial engine is going to be by the cylinder arrangement. All the radial engines connect to a crankcase, just like, or all the cylinders connect to a crankcase, just like it does on a horizontally opposed engine like that we've worked on before. This time, however, instead of having a case that's a big square that cylinders mount to, instead it's in more of a circular fashion that all comes together in the center. Now, the way we start to tell one engine from the next when it comes to radial engines starts off by asking how many rows of cylinders does it have? Well, you can see the R680 is a single or a single bank, was what we call a group of cylinders, a single bank of cylinders, or a single bank radial engine. Now here's a Pratt & Whitney R1830 in 1830, or better known as a WASP engine. It's one of the most iconic engines in aviation history. Now, it's most famous for being mounted to the C-47, which all of the 101st Airborne jumped out of on D-Day into Europe, and then at Market Garden on afterwards. And the WASP engine is what powered that operation. There's two of them mounted to C-47. Now, afterwards, this same aircraft would be put into civilian use, known as the DC-3, and used primarily for heavy lift bush applications and passenger transport. Even today, there is still one airline that still flies a DC-3, and that's Buffalo Airways up in Yellowknife. And they famously made the show Ice Pilots that display the DC-3 being used, powered by the old WASP engine. Now, we bring this up because it highlights how a radial engine can have two separate banks of cylinders. You notice that the WASP has two banks of cylinders, and they're offset one for another. Now, that's to help to facilitate airflow and engine cooling. As air hits the first cylinder, it blows around it and then out the back of the cowling. And then instead of having a gap right there like you see on the R680, the WASP has another cylinder sitting there in between the first and second cylinder of that first bank, which allows it to, the second bank of cylinders, since they're offset by a cylinder's length, to hit fresh air and cool it all down. And then this pattern of cylinder offsets will continue as the bank of the cylinders increase. Now, this is a major Wasp engine. It's a four bank radial engine. As it goes around, you can see that there's that offset of cylinders, and they'll just kind of just a little bit as they go down. Now, radial engines you'll see come in two bank radials, four bank radials. There is one example of a three bank radial, but the kind of cost to benefit ratio of that third bank really wasn't, I guess, as good or as effective, and so the three bank radials really weren't very popular. However, they did four banks definitely came out. So you can see that, like, that's it, generally speaking, there's not a whole lot more to it other than you're just adding components, the same components back to back. Just like adding going from a four-cylinder horizontally opposed engine to a six-cylinder or an eight-cylinder horizontally opposed engine. Nothing to be super duper afraid of or super weird about. Just that it's just going to be more parts pieces for you to inspect and maintain. Okay, so let's talk about a couple of other distinctives that you'll come across in radial engines. Now, the radial engine won't use like overhead cams or anything else like that, like you would in your car. They will always use a push rod system because of the way that the engine is mounted. You think that an overhead cam has a cam that sits over top that pushes the valves down as it goes, makes the engine perform a lot better for efficiency reasons that we'll get into later on in the course. But because the radial engine is mounted on the bottom of the crankcase, and all the movement is happening there, and the head of the cylinder is actually far away from everything, the only way to really accomplish valve movement is through push rods that go up and down. And we've seen push rods before in the previous video, and you can easily see them by looking at the picture of any single any single radial engine that's out there. You'll have to see two long shafts that come up, and all those are just metal tubes that have the rod on the inside. Now, the graphic that we're looking at right now kind of shows you how it works. So you have a camshaft with a cam lobe that comes around, hits the cam riser, and then pushes on the push rod that pushes up on the valve, or eventually, pushes up on the rocker arm that pushes down on the valve to allow air to come in that's been atomized and exhaust to leave. But that's something that you'll see. You'll notice that on all your radial engines that they're all push rod systems, no overhead cams. Now, if we go back and look at our table from earlier, another thing that you'll notice that's something that's kind of fundamentally unique to a radial engine is the crankshaft. It looks like the head of an old derrick swinging around in a big circle. Yeah, so just like the head of a pump jack, you have a counterweight that swings to help kind of smooth the engine out. You have dampening weights and a counterweight, two different things. Dampening weights are help to take care of one harmonic vibration. The other counterweight basically is just that. It's a counterweight. It slows the vibration down. Now, you think if you were to take your tennis shoes and put it on one side of your washing machine and turn it on, it would just shake itself literally to pieces if you let it go long enough. A radial engine does the same thing. These counterweights and the dampening weight are meant to do just that, to help keep it from shaking itself apart by giving a action in an equal and opposite direction to help smooth it all out. Now, on this graphic, while we have it up, we also have a journal, which then will connect. Your crank pin will help connect different counterweights that are arranged to dampen the other cylinders from firing, and the journals basically keep it all in one, or keep it all in line, keep it from breaking loose. And then the crank cheek there is just simply the part that we call the neck that connects the counterweight to the places where the crank pins connect. All right, so the last thing that's really kind of fundamentally unique to radial engines is its crankshaft arrangement, and it's specifically the connecting rod assembly. You can see here as the counterweight goes around how you have one yellow rod that is connected to a hub, and then you have all these other connecting rods that are able to pivot around that hub to make the movement happen. This is called a split type master rod. And we talked about that in the last video. That you have one master cylinder, and you have all these other cylinders or these other connecting rods that are moving up and down their cylinder in a I guess in reaction to where that master rod is going up and down, and that's something that you see on radial engines pretty well exclusively. You could have it in some other places, but for the most part, it's going to be just in radial cylinders because they're the only ones that are set up in a circle like that. But yeah, so that is radial engines. Very common in the older era. If you decide you want to do vintage airplanes or you want to work for like Confederate Air Force, get ready to work on a lot of radial engines. If you decide you want to do de Havilland Beavers and that kind of thing, get to work ready to work on radial engines. But I'll let you know that as time progresses on, those radial engines start to fail. The supply chain's not really there for them anymore, and they're basically getting replaced with turboprop engines, which we'll get to in a later video.
Now, there's a lot of different engine types that are out there. A horizontal engine and a radial engine are just two of them. The one thing that they have in common, though, is they both take unleaded gasoline or leaded gasoline. These will all run off of either avgas, which is 100 low lead, so leaded aviation gasoline, or if they have the right STC, they can run off of automotive gas. Now, there is another type of engine out there that's not run off of gas and it's not run off of jet fuel, but rather is run off of diesel fuel. And because it's run off of diesel, there are certain things that make it slightly different than a regular horizontally opposed engine like you see behind me here. Let's talk about diesel engines.
All right, so at first glance, you don't see a whole lot of difference between the diesel cycle or the Otto cycle, just basically the regular engine cycle that you're used to. Still suck, squeeze, bang, blow. The main difference that you're going to see with diesel is that there is no spark plug, and the reason being is that diesel engines compress their air so tight, so hard that it gets super hot, and then all they have to do is simply just spray fuel into the cylinder, and it auto ignites, and that's what keeps the diesel engine going. It's just steadily goes that way. Now. There are certain engines will have glow plugs in there to help raise the temperature of the air even before the compression stroke happens. You generally won't see that on airplanes. Now, that being said, the caveat is that the diesel market is still young and changing. So if you watch this, it later on and there's glow plugs on airplanes, just know that it probably came after this video was made because it's still progressing. But at the heart of it all, diesel engines are really fairly straightforward, fairly simple, even simpler than your regular just avgas run aircraft engines. There's no magnetos, there's no spark plugs to gap or anything else like that. Simply, you just have to make sure that the injectors stay clean, and everything else is fairly mechanical. Okay, so you may be wondering why even mess around with diesel? Like, why is that a thing? Well, you have to first understand this picture. Now, to the right is a Fish and Wildlife Service Quest Kodiak. The Quest Kodiak was built for the modern day bush application. They took a Cessna Caravan and they basically beefed it up, and they went through and they made little decisions in the design process specifically geared towards flying on remote airstrips in third world countries way out in the middle of nowhere. Now, to the left of it, looks like it's a Cessna 182, I believe, or a 206, one of the two. I'm not exactly sure which, but it just doesn't really matter. The point being is that's the typical bush plane that's been developed for non-bush activities, but it's been employed for flying off airports on sandbars and unimproved strips all around the world for many decades, and it's done just fine. The problem comes into to fruition whenever we start looking at the individual fuels. It is very, very, very difficult to get 100 low lead for aircraft in certain parts of the world, if not totally impossible now. And so operators like Mission Aviation Fellowship, or JARS, or any of the your Bush carriers, they started to realize they were paying a lot of money in gas whenever they could find it. And so they had aircraft that were just sitting on the flight line because they simply just didn't have fuel to get them from point A to point B. So they started to pivot, and they looked at the Cessna Caravan. And so the Cessna Caravan slowly started to replace a lot of the little Bush aircraft, like your 206s, 182s, 185s, those types of aircraft. But the problem is that the Caravan's a large, turboprop aircraft, and it needed to be to sneak into smaller airstrips that normally you wouldn't take a Caravan into. And so the guys at Quest came up with the Kodiak, which was modeled after the Caravan, but was able to have the same performance profile as some of the smaller airplanes while using Jet A. Well, this seemed to solve the problem in the short run. But then the problem with Jet A is that it's still expensive, whereas diesel fuel is actually not that expensive compared to 100 low lead and Jet A. So all of a sudden, there's sort of become this emerging market where it's like, hey, look, I don't have the money or even the need or desire to operate something like a Kodiak or Caravan, and fuel costs are really sensitive to me. Is there a better way to get around? And that's where people started really looking heavily into, could you make a diesel fueled aircraft? And the answer is yes. All right, this is the E4 series diesel aircraft engine that goes on Diamond aircraft, the AE300 and AE330s. Now you can look at this and you can notice a lot of really common nomenclature that carries over from reciprocating engines, like an oil filter, air intake manifold. You'll have high pressure fuel pumps, generators, oil coolers, and look at that, even a glow plug control unit. This engine actually has glow plugs on its aircraft engine, and they are fairly common at this point. They are you'll see them on, like I said, on Diamond aircraft. They're able to run at much lower operating cost on a much more easily acquired fuel that's out there. And you're going to start to see more and more of this as time goes on. Now, we still have a lot of legacy aircraft that are out there running on avgas, but avgas is expensive. Even on the field today, it's like $6 a gallon, whereas diesel is like 4, and you can get diesel just about anywhere. And so, like, you don't necessarily have to have a special pump or a special supplier that to bring you that aviation gasoline. You can get it simply at your local convenience store, and put it in your engine and go, which solves a lot of problems. It's cheaper, it's more available for these remote strips, and it actually produces a fair amount of power with a little bit less complexity that you have on your legacy internal combustion engines. Now, that doesn't mean that they're going to just completely take over everything. You're going to see probably, my guess is you're going to see more and more turbine stuff than you will diesel. But eventually, like the 100 low lead and automotive gasoline engines will probably go away. And they're already very hard to come by new engines now, and even harder to get the old ones reworked and overhauled and put back into, especially if you have something seriously wrong with it. And so, just if you are going to be a GA guy, it may do you well to spend a lot of time getting to know the diesel side of things. Now, I'll tell you, because we're focused on heavy commercial aircraft, we're going to spend a lot more time in turbine engines than we will on any piston engine that's out there. But if I were going to be a GA dude for the rest of time, and I wanted to set myself up for future, I would look heavily into getting some FAM courses done on these diesel engines because they're going to be the future. At some point, you're going to see more and more of them and less of the 100 low lead crowd.
Now, this R680 is a very old engine. you can see that it was actually originally produced in 1945. Now, that's a long time for an engine to be in existence. It's almost 100 years. That's almost the entire life of aviation as an industry in and of itself. How do we keep engines preserved and stored so that way we can pull them off the shelf and put them right into service?
All right, so this is an IO 540. It's a very common aircraft engine that you'll find on higher performance aircraft, like say the Aztec, Cessna 182. Those types of planes. It's still in the general aviation, definitely not into the realm of turbine level performance, but higher performance nonetheless. Now, this one has been pulled off because you can see that cylinder there has been damaged on the bottom right. I believe it's the number one. And it's going to go off to get overhauled and taken care of. Probably get a whole new jug put on it. But let's say that we were going to we sent it off to an overhaul facility and put a brand new engine on, and then all of a sudden we got one back. What would we have to do to make sure that that engine is taken care of? And so what we're going to do is we're just going to go through the procedure for storing this engine per the IO 540 series engine installation and operations manual. And you'll find very early on that the main thing that you're trying to combat against is corrosion. This is directly out of the manual. It says the life expectancy of engines in aircraft that are not in flight frequently, flown at least 1 hour within 30 days, can decrease because of engine corrosion. Engine corrosion occurs when moisture from the air and products of combustion stick to cylinder walls and bearing surfaces when the aircraft isn't used. Corrosion rates can increase because of variable factors as environmental conditions, humidity, salt in the air, ocean areas, seasonal changes, and in engine use. So since conditions can change, the corrosion rate can change. And aircraft operating in close to oceans, lakes, rivers, and humid regions have a greater need for engine preservation than engines operated in arid regions. In regions of high humidity, corrosion can be found on cylinder walls of new inoperative engines in as little as 2 days. That's pretty quick, just for it to start corroding inside of 2 days. Whereas in less humid environments, cylinder walls on engines that have 50 hours or more time in service within weeks can varnish coating that will protect them from corrosive action. Such engines under these atmospheric conditions can be inactive for several weeks without evidence of damage by corrosion. Engines that are in flight only occasionally less than one time per week are more at risk for corrosion. Now, that's a high standard for your little GA airplane to be flown that much. Especially if you'll see a lot of these old guys, they'll have engine or have aircraft they only fly every once on blue moon just because simply they just don't have the cash for the gas. So what do we have to do to set this engine up for success if we're going to just take care of it and then put it on the shelf? Okay, so the first thing that you're going to do is you're going to service it with a preventive oil mixture. It's going to be 1 part by volume, Mil C 6529 Charlie Type 1 concentrated. Now, this is just an example from aircraft. So there's this aviation anti-rust oil, but you're going to put that type of oil in the engine to keep it from starting to rust. Now, this oil needs to come out whenever you return it back to service, and there's a procedure for that. You just follow in the maintenance manual. But to set one up and just set it on the shelf and let it sit for a while, you're going to need to first service it with some sort of anti-rust engine oil. All right, the next thing you need to get your hands on is going to be a airless spray gun. So this is basically going to allow you to spray preservation oil into places that it needs to get. The next step is going to be get these desiccants. So these are like little clay desiccant bags you can get from a variety of different vendors. This one's from Uline. And you're going to place it in different spots on the engine. You can also get spark plug compatible desiccants that basically you screw the spark plugs out, you screw the desiccant in there, and that helps absorb all of that extra moisture that may be in the cylinder, so that way it doesn't allow for corrosion to begin. All right, so basically all you're going to do is run this engine up once you've got all the parts and pieces assembled. You're going to run it up You're going to shut the engine down. You're going to drain the engine oil while it's still hot, try to get all the gunk that's out. You take the oil filter off, put a new oil filter on there. You're going to service it with the anti-rust oil. Take the spray gun. You're going to spray that anti-rust oil in there. You're going to clean out the oil screen before you do all that, obviously, with mineral spirits, and you're going to try to get it as clean as possible, and then place those desiccants in places that where the moisture may start to start to affect the engine. So all along the tops of the cylinders, next to anything that could potentially corrode or oxidize, and ideally you have those spark plug compatible desiccants that you can screw into the spark plug holes after you've applied the anti-rust spray with the spray gun into the cylinders itself. And basically all that's doing is just keeping corrosion from setting in. It's not really that difficult to do. You'll make sure that you put the desiccant in the intake pipes, in the intake ports, and ideally, if you can, put them in the along the exhaust ports as well, and that helps pull all of that excess moisture out. Other than that, then at that point, you're going to crate it, stick it into a place that's not going to be too humid. It's not going to get too hot. It's not going to get too cold. And then you're still going to have to maintain this engine. You can't just just forget about it. It's not like something you just put on the shelf and off you go. You're going to have to look and say every 180 days, every 90 days, every 60 days. What do you have to do to check different things? And if you find corrosion or whatever, you need to figure out how's the corrosion getting started, and then take action to mitigate it. Other than that, preserving the engine's pretty straightforward, and preserving a turbine engine is about the same thing. It's a little bit, in my opinion, is a little bit less work, but that being said, it's the still things. You can go out to our JT9s right now and see that there's desiccant bags in its tail to help try to pull any extra moisture away from the engine, and because they are technically in storage, they're being preserved right now. But yeah, so that's all for this video. We'll see you in the next one.